talk about transaminases again? Or no, we talk about. So what's the other way to get ammonia into amino acids? So the alpha amino group of glutamate and the side chain of glutamate, which becomes glutamine. Right. So yeah. So alpha ketoglutarate you can put on the alpha amino. You got glutamate, and then you can add on to that the glutamine. I think we talked about that, didn't we? Because then there's also how do you move these amino groups from one cell to the other, from say muscle to liver, right? And there were two ways to do it. And glutamine, right? And so we were talking about, glutamine's an ideal carrier because you get 2 for 1, right? If it were just glutamate, you just have the alpha amino, but you say, and as in the case of alanine, but with glutamine you have 2, so that's likely why that's an efficient carrier then. And glutamine then is of interest because why? What, in addition to being a carrier, what other role does it serve?
The ammonium group it carries is non-toxic.
It's a non-toxic form for biosynthesis. So the first one we encounter in this lecture is what? What do we synthesize with the side chain amino group of glutamine? Asparagine. Right, so we make the counterpart amide just with that because it's a non-toxic way of doing it. So in the active site of the enzyme, it releases it, and then we see it twice, right? In where? Where do we see the side chain of glutamine used instead of ammonium? So it's released as ammonium, but it's trapped in the active site. So we see that.
You create asparagine, right?
We see it twice in purine biosynthesis and at least once in pyrimidine.
And that's why it's asparagine?
No. Glutamine. The side chain of glutamine.
No, I'm saying like to create asparagine you use glutamine, don't you?
You do. So that's the first place we encounter it. But then subsequently we keep encountering this phenomenon.
To raise the amino.
Hello? What?
To make the ring.
Yeah, for the ring. So you'd like to start to, and so in pyrimidine biosynthesis, that's the source for the carbonyl phosphate. Right? Remember that whole thing, carbonyl phosphate synthase? It's glutamine there and it's released and it goes through the channel. So it's non-toxic because this is in the cytoplasm. And then we see it again for purine biosynthesis for the ring twice. Right? It's what starts it off. We have activated. That's how we make a purine ring, as we start out with the phosphoribosylate pyrophosphate, and then we put on the first amino group, and that comes from glutamine. And then later in the ring, we do that again. So that's at least 4 examples that we ran across. So that
I was having a question. You said it's not toxic, glutamine, but I thought the reason why you got the osmotic pressure defect was from a built-up.
Right, but in this case, it's just it's a fleeting intermediate that's trapped in the active site of the enzyme. So it's released there, and then it's immediately consumed in the reaction.
Okay, so it's just better than free.
In the cytosol, yeah. Okay, yeah, that's a good point. So, I don't know, I'm kind of all over the map here. So where were we? Were we going anywhere? We're in biosynthesis. We just made asparagine. So we made glutamine. So we made glutamate, glutamine, asparagine, and now we're just walking through. These are the ones that stand out to me because they kind of make sense. They're right. So these were all one-steppers, right? There was that business too. The ones we can make are the ones that are simple, and there were maybe 3 that were one-step. So
Can you talk about the synthesis of proline and arginine from glutamate?
Well, what's after? Somebody wake me up. Amino acid biosynthesis, right? Okay, God, we're at
acetate goes to
glutamine, asparagine. What's the next one?
Arginine and proline
From
Really?
the next slide.
From glutamate.
Give me this bad look.
Is it? No, really?
Yeah.
Arginine and proline?
From glutamate.
Okay, and so what do we know about arginine? It can be done in, yeah, so it's 3 steps in the urea cycle. So I just like to kind of skip ahead. But as well, then there was this funny, what is it, gamma glutarol semialdehyde or gamma, is that it?
Glutamate gamma semialdehyde.
The common intermediate, what's its name?
Glutamate gamma semialdehyde.
Glutamate semialdehyde, isn't it a gamma in there?
Yeah.
Glutamate gamma semialdehyde. That's useful, isn't it? Anyway, a common intermediate because it's an aldehyde. Okay, so it became an aldehyde. Is that the alpha the carboxylate at the alpha carbon, or is it the side chain where we made this aldehyde from glutamate? Side chain? The side chain becomes an aldehyde? Yeah. Yes? Okay. So side chain becomes an aldehyde. So that then allows us then to readily make proline. Right? It has to be the side chain, doesn't it? Yeah, because that's why we have this funny side chain of proline. So then it's just a simple nucleophilic addition at that aldehyde, and then you're almost done. So that's proline. And then that same intermediate can give you arginine in a much longer pathway. Okay, so that's all I know about those two. It's about all I want to know about them. Okay, who's next?
The side
Rachel?
chain is reduced.
The side chain is, of proline. You got to reduce it. Okay, that seems reasonable. Did you have to get rid of the water? Is that why? Does an OH goes off?
Just the
Yeah. So water goes away, so you have to reduce it. Yeah.
It's an NADPH.
Okay. So now you know more about it than I did.
Next one is serine.
Yeah, and they'll say that, the point being you don't need to know all that. But it's good that you can see it. Oh, that's good. Okay, next one is what?
Serine.
Okay, so serine. We all care deeply about serine. Why?
Because you can make glycine and your N5 and 10 methylene.
Your one carbon. So source of your one carbon that came originally from glycolysis.
Can she say that?
You need that serine in order to form your glycine and your N5, N10 methylene tetrahydrofolate.
AKA one carbon.
Yeah, that thing you use in pyrimidine synthesis.
Yeah. Partially true.
Well,
Why is that partially true? Do we use that method?
well, it's a decoration.
It's a decoration and it's a different oxidation step as well. But it's still a source to get there. But it's a decoration because when we make purines, we use formal, and they're actually part of the ring, right? Whereas for pyrimidines, it's a decoration to do what? To make the T, so that we got the D. Yeah. To make thymidylate, so we can have DNA. So that's why biosynthesis of serine, that, we're happy about that. We're fortunate that we can get to serine from glycolysis. But there's an amino group that we've got to have an amino group. Where does that come from? Is it glutamate? Okay, seems reasonable. But I was going to say it's a transamination. So that's a weird transamination because it's not a alpha keto acid that we're familiar with. Doesn't it have a funny name like something pyruvic or